AI for Content workshop. So next talk will be from Professor Tali Dekel. It's my great honor to introduce her. So she is an assistant professor of mathematics and computer science at the Weizmann Institute of Science. She is also a research scientist at Google. She was a postdoc with Professor Bill Freeman at MIT. Professor Dekel has received many prestigious awards, notably Best Paper Award from SCCV and the Best Paper Honorable Mention from CVPR. So without further ado, let's hand it over and for her talk.
Thank you. Hi. Seems I'm not able to still share screen. Guys?
The Jane's working on it.
Oh, okay.
Okay, it should work now.
Okay, great. So let's see. All right. Hi, everyone. I'm thrilled to be here, and thanks so much for the introduction. So today I'm going to talk about analyzing and re-rendering everyday videos, which means that I'm going to play lots of videos that are not going to stream very well on Zoom. So please also check out the videos later offline. So videos are all around us. We are all capturing our dynamic world somehow through videos and share them in different ways. For me, most of my videos are of my children. I take many of those videos, and I really care about those videos. But even for me, those types of videos could get really boring, and I hardly watch them. So recently, I've been quite interested in how can we take everyday videos and make them much more fun, engaging, artistic, or more generally, how can we enhance the way we can perceive our dynamic world through ordinary video? So just to give an example, so here we told the kids to jump to the pool together, but of course that each child jumps to the pool at a different time. And to tell kids to do what you want is an impossible task. So what I'm going to show you next is a result that we produce computationally and automatically as a post process in which we retime the motion of those children such that they all jump together to the pool at the same time. So this is achieved as a post-process of the original video. And now notice how not only the children are retimed, but also all the scene elements that are related to them, their reflections, the water splashes, everything nicely follow the children in the retimed result. Okay, so going into the video and changing the timing of individual people is one effect that we might want to apply to our videos in order to enhance the way we can perceive events in the video. Another example, so here is a well-known video of a horse jump, and we can create this kind of like panoramic and stroboscopic type of a video out of it. And again, you can see that not only the horse is being duplicated here, but also the shadow is nicely casted below the horse and each kind of like duplicate. Another useful effect that we might want to apply is actually to remove objects from the video. So here we have a bunch of people jumping and causing complex deformation to this trampoline. And we want to be able to get this result, like remove everyone from the video except, let's say, one person. And again, here you can see that also all the deformation effects that the other people caused are also removed from the video. So when you think for a second, what is required to produce all these effects that I just showed you, think about it for a second. Clearly, we have to segment out the objects, but it is not enough. We also must take into account all the scene elements that are related to the object and edit those as well. And actually, computer vision has become really good at segmenting objects in video. So what you can see here is a MassCar CNN, a state-of-the-art kind of like segmenter results on this video. But if we want to remove those peoples and we plug in those masks into a state-of-the-art object removal kind of like algorithm, this is the result we get. Again, because we're not modeling the scene effects that the people generated in the scene. So video editing and these applications that I just showed you, they pose a novel research question, which I think is very beautiful. How can we associate objects with all the scene elements that are related to them, varying scene elements that could get really complex in a video. And that kind of like led us to a line of work that I'm going to talk in more details next. First, we tackled this problem of associating objects and their effects in videos in the context of retiming people, and that kind of like led to a human-specific model. And in this CVPR OmniMat work, we generalized our approach to deal with generic objects. And if time permits, I will also highlight a new work that we haven't released yet that also deals with everyday videos. But the goal there is to estimate depth of dynamic objects in video, and that gives rise to all sorts of like depth-aware effects that we can apply to videos. Okay, so let me start with our SIGGRAPH Asia 20 work, where again the goal was to retime people. This work is in collaboration with an amazing group of people, and Erica Liu, who interned with us in the past couple of summers, and Forrester Cole made this project possible. So again, we want to alter time of individual people and consider this video, for example. Again, in order to get a realistic result, we must also retime the effects. So for example, the reflection on the glacier, if we want to change that person's timing in the video. Another challenge that the retiming effect introduced here is occlusion. As you can see, when we will retime a person in the video, we might reveal some regions in the video that were occluded, like the person here in the back. And in order to create a realistic effect, we must realistically synthesize those disoccluded regions. And the way we tackle this problem is through a novel layer decomposition of the video. This decomposition is human specific. What I mean by that is that each layer is associated with a person and all the scene effects that are related to that person. We also have a layer for the background. Another key feature of this decomposition is that each layer provides a full body estimate of that person, even if they are occluded in the original frame. We assume here that the depth ordering, by the way, is kind of like known between the layers. Okay, so you can see that the person is occluded in the frame, but this completely disoccluded in the layer. Okay. So now that we have those layers, we can apply a bunch of different editing effects by simply manipulating the layers themselves. So for example, we can remove a person from the video by simply not rendering their layer. And again, the reflection on the glass is also removed. The task of decomposing video into layers is not new. The pioneering work by Wang and Adelson inspired a great body of follow-up work throughout the years. Recent method, of course, use the power of deep learning, like this work from Noah Snavely's group. Here they take like a stereo pair with a narrow baseline, and they estimate layers that corresponds to physical accurate depth in 3D with the goal of synthesizing a novel view of a static scene. We also use the power of deep learning, but in our case, our layers are not meant to be accurate in terms of depth. In our case, each layer corresponds to a person and their scene effects, and our model is actually trained on a single video without observing any additional examples in a self-supervised manner. So the main driving loss that kind of like drives this optimization on a single video is a reconstruction loss, where we want the layers, when we composite them back together, to allow us to reconstruct the original video frames. Now I'm going to tell you more about the model, but I won't be able to go into all the technical details, but it is important to me to give you kind of like a high-level intuition about why it works and how it works. So I hope that will go through. Okay, so we have this model, and this model works in a frame-by-frame manner. It takes a frame and it outputs a set of layers. We have one layer for the background, and again, one layer for each person. And each layer is represented with a color image and an opacity map. So the first question is, how do we associate a layer with the person in the video? How do we tell the network place the left person in the first layer? So the way we do this is by representing the people and a static background explicitly and providing it to the network as input. So these days, there are plenty of methods that can be used to compute geometry and appearance of people in images and videos. And we were able to use off-the-shelf techniques like dense pose with combination of our own techniques to create like a representation of people and a static background that we pass into the network. Now, I'm not going to go into the details about exactly what this input is, and it's also not that important. What is important to note here is that the model has to do kind of like a good job at reconstructing the video. In order to do that, it must also reconstruct all the time-varying scene elements in the video, like this reflection here. But this reflection is not given to the network as input by any means. So all the time-varying scene elements like reflections, shadows, and so on, they has to be inferred automatically by the network, while we provide an input that only represents the person and a static background. Okay, and I'll recall that this network is overfitted to that single video. So it has to memorize this reflection from the input that we provide in some layer. So by doing that, we kind of like force it to place this reflection in one of the layers. It cannot place it in the background because we assume that the background is static. So it is forced to place the reflection in one layer. And a key question here is, what is the magic that will cause this model to place this reflection in the right layer? What will cause it, to place this reflection in the layer of the person causing it? And now we all know that networks are really powerful. And when they are too powerful, they could do random things. So we wanted to prevent that and steer the network towards the solution we want. And the way we do this is by limiting what the network can observe about the scene by feeding it only a single person each time. So basically, the layers are predicted as in a separate forward passes into the network. And now to understand why this is important, let's take a look at this reflection again. Again, the network task is to predict this reflection from the input that we provide. And it can predict it given the left person's input or the right person's input, okay? And now if we take a look on this task over time, we can clearly see that there is high correlation between the left person's position or representation to its reflection. By knowing the input of the left person, we know a lot about the left person's reflection, okay? So there is high correlation, and it's an easier task for the network to predict the left person's reflection from the left person's input. On the other end, the right person doesn't tell us much about the reflection of the left person, and so it's a much more difficult prediction task for the network to do. So in short, the reflection can be learned quicker and in fewer iterations from the left persons, and that's the solution that the network favors. So this is kind of like a very intuitive explanation. I will exemplify this through some toy examples soon, but just to wrap up kind of like the method part, we apply several training losses. As I mentioned, the reconstruction loss, we want the layers when we composite them back together to allow us to reconstruct the original video. We also have regularization terms on our alpha mats, encouraging them to be sparse. And also it turns out that these two losses were not enough to make the optimization converge. So we also had to bootstrap and initialize our alpha mats by kind of like encouraging them to match a rough segmentation mask that we can compute using off-the-shelf techniques. And we turn off this loss after several epochs and let the optimization kind of like refine those. Okay, so let's see this intuition that I just explained through very quick kind of like toy examples. So here we have a very simple scene. We have a person walking over a background. Actually, we don't have any scene effects here. And I'll next show you the training progression. Okay, so what you can see here is the original video, and next to it you can see like the rough segmentation mask that we use to initialize the network. And now you can see that as the training progresses, the model kind of like learns to add details that were not represented by our input. It kind of like gradually refines the rough segmentation mask that we kind of like used to bootstrap and adds on details to the network. Okay, so now we added effects. We added two squares. One is correlated with the person and the other one is randomly moving. And now let's take a look at the training progression. So what we can see here is that first the person is learned and the details are added, and then the correlated square. And then after many epochs, the randomly moving square is reconstructed. So basically what we can see is that correlated motion is learned earlier than uncorrelated motion. Similarly, now here we look on spatial proximity. We took two squares, they are both moving along with the person, but one is farther away. And again, if we take a look on the training progression, we can see that first the person is learned, then the nearby square, and then the farther one. So nearby effects are learned earlier than distant effects. And finally, if we have two people, each one is kind of like has its own correlated square, and we assign a different layer for each person using those tri-maps, as you can see. So here too, first the people are reconstructed, and then each person kind of like grab is correlated effects earlier in the training, okay? And this finding might not be surprising if you're familiar with the deep image prior work, where they basically show that, you know, if you try to fit an image into a CNN from scratch, it's a much easier task to fit a natural image than a random noise image. And in natural images, the patches has like these high correlations between themselves. So it's an easier task for the network to fit. And in a similar manner, in our case, the effects are space-time. They are correlated with our inputs in space or in time, and therefore effects that are correlated with the input are learned faster. So let's see another example. This is again a fairly complicated scene, and here we used our method to freeze in time one of the couples each time. And again, we can handle well with all these complex effects on the ground and occlusions and so on. Here we actually assigned a layer, one layer to each couple. I'll show you the breakdown in a second. So here you can see how in the first row, you can see the initialization, basically what we use to initialize the network. In the second row, you can see kind of like the alpha maps that our method estimated and grow, and you can see how it add all the fine details like loose clothing and the reflections on the ground. Okay, so we really got excited about this ability of the model to associate people with their effects. But an obvious limitation of this model is that it's human specific. We used kind of like off-the-shelf, kind of like human-specific parametric models to represent the input to the network. And so we wanted to generalize this, and this is the work that the OmniMet work that I'm going to talk about next. It's presented at this CVPR, and we wanted to to get this ability of associating objects with their effects, but work with generic objects. And we still wanted to kind of like, you know, utilize and leverage this property of this network to be able to associate, to find correlations in space and time, like we did in the retiming work. So we were looking to replace those human-specific inputs with a much more simpler and accessible input that could work on a wider range of objects. And that kind of like led us to this setup where, and to set this novel problem of, you know, estimating omnimets, and I'll say in a second what I mean by that. So we're given an input video, and we have a rough segmentation mask that you can get using off-the-shelf techniques like mask-R CNN for each object of interest. And now the goal is to take this input and produce an RGBA layers, which we named omnimets, that contain not only the object, but also all their scene-related effects, like you can see here. A nice thing that you can see about this decomposition that we actually managed to kind of like fill in the shadow of the kid here, although it is kind of like occluded by the dog, which is a kind of like a nice demonstration of this power of the deep image prior property. So it turns out like the OmniMet work really is quite simple relative to the retiming work, because the key observation was that we actually don't need like very complicated inputs to the network. We can actually replace our human-specific UV maps that we used as input to in the human case with rough segments and optical flow. And we can still keep the same training paradigm and everything the same. So this is an overview of the method. For each frame, we have kind of like a rough segmentation masks for each subject or object of interest. And we also compute optical flow fields with respect to consecutive frame. We have our OmniMat model. And again, the layers are feed forward in a separate forward pass into the network. And the network predicts an RGBA layer. And we also here added, the model also predicts like optical flow layers. And we added the prediction of the optical flow as kind of like an auxiliary task that inject information about motion into this model and improves the decomposition. So again, the same trick, the same kind of like blinding the network and preventing it from observing all the information to do this association of effects with the input. For the background, I just want to mention that we assume a static background, but we can handle camera motion that can be represented well using homographies. And the way it works is that we align the background to the same coordinate system using homographies, and then we predict a background layer which is panoramic and looks like that. The input is just kind of like a fixed noise image. We predict a panoramic background layer 1 for the entire video, and then the background for each frame is just kind of like being sampled from this panoramic image using the pre-computed homographies. So we can handle camera motion that can be represented well with homographies. Okay, so again, we haven't changed much from the retiming work. We just simplify the input. It's the same training paradigm, the same kind of like intuition, the same property of the image prior property of associating and correlations using this separate forward pass into the network. In terms of training losses, we still have the same training losses that we had in the retiming work. So we still want to be able to reconstruct. This is still the main loss. We want to be able to reconstruct the original video frames from the layers. We have the regularization terms on the alpha. We have the initialization loss that we turn off after a few epochs. And we also have, because we added flow, we also have 2 additional losses. One that kind of like is a flow reconstruction loss, which is similar to the RGB reconstruction loss. So we want the predicted flow layers to match the pre-computed optical flow when we composite them together. And we also have like an alpha consistency loss, which is based on warping, based on the pre-computed optical flow. So I'd like to show you a couple of results. So these are results from Davis. So as you can see here, we managed to nicely capture the swan along with the reflections in the water. In the second example, the elephant throw semi-transparent dust that we can extract quite well. And in the horse example, we are able to get the shadow very clearly and nicely here. You can see that the shadow is not visible in the background layer. If you take a very close look, you can also notice a few artifacts. So in the swan example, in the background, you can notice a piece of the swan in the background, and that's kind of like that's a region in the background that we never observed behind the swan, so the model doesn't know how to complete it. And also in the elephant case, you can see that not all the dust is kind of like in the foreground layers. But overall, these results are quite compelling, and they allow us to do all sorts of effects, as I'll next show. And this is just to compare with the retiming work and to show you that we didn't lose much by changing kind of like the input. So the second column is the retiming work, and the right column is the OmniMat result. And you can see that actually the layers are cleaner, and that's because we also model some deviations from a completely stable camera. I didn't talk about those details here, but check out the paper for more details. So I'd like to show one application, a real application. We were given this video and we were asked from a team in Google to place a logo on the background on the ground below the semi-transparent smoke of the car. And here is the result. And here is the foreground layer. And the cool thing is that you can actually notice the shadow of the smoke in that layer, which it's very hard to see in the original video. Another cool effect that we can apply is a color pop. So here we kept in color only the flamingo and the reflections. Okay, so I just want to conclude with a small highlight of a new work. So this line of work of decomposing video into layers, it was really exciting to me. But one thing that we don't model is the scene geometry. We assume known depth ordering, and we don't assume we don't model the geometry of the scene in any way. So in this CGRAPH, this coming CGRAPH, we have a new paper where we address the problem of estimating depth of moving objects in everyday videos. And this is also a joint work with Jotong and Forrester and Richard and Bill. And actually, I started working on this problem also in the context of people specific. So in CVPR, we developed this model that could estimate depth of moving people in cases where both the people and the camera are freely moving. And in this case, geometric constraints break. We cannot use triangulation, and we use the data-driven approach to solve this problem. Specifically for humans, we were able to get like really cool source of training data and get like ground truth and get state-of-the-art result. But this model was specific for humans. And again, we wanted to generalize this to deal with generic moving people and get also temporally consistent depth map. This model was only working on 2 frames. Again, I am really behind time, but I just want to kind of like show you that if you take this video and you kind of like use multi-view consistency losses to compute depth, you will end up with fairly large significant errors for the dynamic object in the depth map. So this is a result of a recent method that optimized depth over a video. So you can see that the depth maps are really kind of like temporally consistent for the background, but the foreground objects are kind of like all messed up. So in our case, we were kind of like targeting specifically this task, and we were, and the key idea here is that we want to model the motion in 3D of dynamic objects and apply some motion priors to handle the ambiguity of depth and motion in this context. Our model is also being overfitted to a single video, similarly to the OmniMat and the CVD paper, and this is the result we were able to get on this type of video, and that gives rise to all sorts of depth-aware video effects. You can insert objects into the video, like here, or you can even insert light source into the video in a depth-aware manner. Okay, so I guess I'll just want to thank all my collaborators and thank you. And I can take questions.
Yeah.
Sorry, I have this itchy throat. Just a second.
So Dejin, you want to take the question?
Yeah, I think, yeah, Lu, you can go ahead. Or there is one question in the chat.
Yeah. So very interesting talk. I think there's a lot of interesting application. Yeah. So we do have one question from Neda in the chat.
Yes.
So have you ever tried with cases I think that's talking about your first work, with the cases that the two persons are working side by side and hence the reflection are side by side. And then
Yes.
each person will be highly correlated to both reflection.
Yes.
Then what should we expect the output
Yeah.
from this now?
Indeed, this is a more challenging case. And if the two people are kind of like correlated with each other. So we've seen two things. We've seen that motion correlation is a cue to the network, but also spatial proximity. So I think if the motions are all the same, then the spatial proximity should basically kind of like determine the composition in this case.
Okay. Cool.
Okay.
There's another question. Like, so the constraint of the alpha matting based model
Yes.
is what is the constant of the alpha matting based? Yeah.
Okay, so we wanted to prevent, if we don't have any constraints, then the entire scene content could be represented by the layers. And we wanted to prevent that. We wanted the model to place everything that it can in the static background and only model what it cannot represent by the static background. So for that, we wanted to encourage each of the alpha mats to be sparse, to have many zeros. So the loss that we used is kind of like a combination of an L1 and an L0 regularization on the alpha mats of each layer.
Oh, sorry. I think they talked about the limitation. Is there the limitation of using?
Okay, limitation. So I guess one limitation is that this is still an output of a CNN, so it will tend to be blurry. And I think that if you kind of like think of image mapping as a model being able to kind of like, take each hair and segment it out, it's not really the case here because we didn't focus on getting like super crisp, sharp outputs. So I think there is still kind of like work in that area that if you want to get like very high resolution and very crisp boundaries of those alpha mats, there is still work to be done there.
Okay, so I have a question. So when you plot these two green boxes to visualize what has been learned first, I'm curious why the person is always learned first than the green box. It seems the green box is easier, right?
Oh, because you need to think about the input that we give the network, right? Like the input to the network is a representation of the person. So it already kind of like has a strong bias towards the person in that stage, right?
Okay.
We are giving it an input that represents the person. So it's much easier for the network to learn the person first than some other elements in the scene. Okay.
So if you give the same input to your second work, then the box should be learned first, right?
Yes.
Then you don't. Okay. Okay, that makes sense. Yeah, I really like those example to illustrate what networks is doing. Yeah.
Yeah, I tried to squeeze them in. I hope it wasn't too fast.
Yeah. Maybe one quick last question. So what do you expect this extend to dynamic motion such as fires, water flow?
Oh, like if you want to kind of like segment out, like, I'm not sure what's the setup. Like you want to segment out or kind of like break the video into kind of like motion layers that represent waterfalls and so on.
Yeah. So I think a complex motion like this.
Yeah, I don't know. It's a good question because again, what we utilized here is kind of like the correlations in motions and so on throughout the video. So it depends on really what is the goal. Like the fact that we're able to in-paint behind the background is because we've seen the background in all sorts of cases from different angles. I think that in order to deal with kind of like these types of motions, you need to inject to the model more explicitly a motion prior that kind of like characterize the type of motions that that are going on in the scene. Maybe some second order statistics on motions or things like that. Okay, great. Thanks for the speaker and yeah, Deqing, you want to proceed? Thank you.